Okay, it's 2 o'clock, so let's get started. Just a quick announcement. Quiz 7 is out if you haven't seen it, and it asks some really cool questions about PDA, so I would highly recommend looking at that. It's due Saturday, just like always. So, are there any questions before we start? No. Midterm, homework 3, anything about class? I like your shirt, Ryan.
I like your shirt.
Thanks. But really, any questions? Actually, that wasn't a question. Anyway.
Are we going to get a cheat sheet on the next exam?
That's not my decision.
It's over decision? Okay.
You can petition for it.
Yes. We should everybody. Yeah.
So, again, not my decision.
Okay.
So, now you know what to do. Any other questions? Okay. So, before all the fun of spring break and all that, before we got every single bit of 355 that we taught up to that point, what did we talk about before spring break? Yeah, PDA. So, what does this 3-letter acronym PDA stand for?
Down, automaton.
Push down, automaton. All right. Not public display of affection, but PDA. Push down, automaton. And informally, what are these things?
There's a machine with memory.
Right, so it's kind of like an NFA, but what other component added to it?
Stack.
Yeah, the stack thing. So, I'd like to define it formally. How am I going to define this formally? Well, how many things were needed for an NFA?
5.
5. So how many do you think this will need? 6. Okay. So maybe the 5 pieces will stay the same. I have state, input alphabet, I have transition function, start state, final state. Same as before. But so what can go on the stack, first of all? Do I need to push only or pop the things that are in my input alphabet, or could I have other things? I could have other things. Could I have the things that I push on the stack be completely different than my input alphabet?
Yes.
Yeah. So what we're going to do is we're going to allow you to have anything you want on the stack. It could be the same as the input alphabet. It could be totally different. Okay. Well, that's nice. I know what finite set of state is. I know what input alphabet is, stack alphabet. I know what the start state is. I know what final states are. So I think the only thing we need to define is the transition function. So let's define it. Well, what thing is always in the transition function for a machine? Before even we look at a character. What are we in at a given point? In a state, yeah. So we always will have a state that we're in, and then since we're doing transitions between different states. Well, what about the input? So how should I define the input part? Do we always have to read from the input? No. No, because this is a generalization of an NFA. So how do I write, you can read from the input or not? How do I write that? There's something with epsilon, but as a set, I'm going to say that it's the input alphabet, but union with it is the set containing epsilon. So I could take a transition which reads a character, or I could take a transition that doesn't read a character. But now I got to worry about the stack, because we have these, I got to put things on the stack, you got to take things off the stack. So what kinds of operations do I need for a stack? Push and pop. What about, say, peek? I mean, I could say you could peek if you want to, but could I define peek in terms of push and pop?
Yes.
Yeah, how would I do that?
Pop
Pop and push, but the problem there is I may have an empty stack. So And if I try to pop an empty stack, then the whole machine goes away, right? So I have to push that pop, but essentially I can simulate peak with push and pop. So the only things that we need then are push and pop. But we need to figure out which one do we have to do first, or could we do them in either order? So if I have a transition which pushes and pops, which one should I do first?
Push.
Pushes and pops. I should do pop first. Why? Because if I push first, the thing I wanted to pop is now below the top. Can I access something other than the element on the top? No. So I need a way of saying that I can pop first, then I push later. But like with the input, could I possibly have I don't pop anything? Yeah, we can make that generalization just as well as here. So I'm going to say that we can have a thing that's popped or not. So remind ourselves that this is popped. Actually, we have to have this here. We can't ignore it. And why is that? Consider a PDA which a PDA which pops on every transition. What does the stack start out as when a PDA starts up? It starts up empty. So if every transition pops, what has to happen? I can never execute a transition. And that's a problem. So I have to allow this here in order to get the languages I wanted to. Okay? What about the output of the transition function? What do I have to have there? State transition to?
Another state.
Another state. So I better have a state there. And now I gotta include something about pushing. Could I push nothing? Yeah, just as well as I could pop nothing, I'll push nothing also. Okay, and also that this is push. Okay, is there something missing here? Rhetorical question.
From popping everything, leaving one thing in there.
It's not about like what the stack is, but in terms of the transition functions definition. How many states can I go to via this definition? I'm in one state, how many can I go to? How many states can I choose here? Exactly one. But isn't this a generalization of an NFA? How did we do multiple states or zero states with an NFA? A set, and how did we accomplish that? Power set. So maybe we can do the same thing here. So the power set of that. So essentially saying we can go to any number of states. Just as like we did with an NFA, I'm going to do it with a PDA. Okay? Cool. Here's actually a really good question. What if I had a PDA that only pushed and never popped? What is that language of that PDA? Well, if it only pushes, does it ever inspect its stack? No. So do I even need a stack at that point? No. So if I have a PDA which only pushes, I only have an NFA essentially at that point. So whenever we talk about language like this, first of all, is this language regular or not? Please say it. The right answer. Yeah, it's not regular. And what string should I pick? What if I chose this string? Would that work? No, why not? Yeah, P can be odd, and I can fix that by either putting a 2 here or saying the integer, the next even integer above it, one of those ways. But if I have a PDA which only pushes and never pops, then I'm in trouble. If I have a PDA which pops and doesn't push, then I'm also in trouble. So if I want to make a PDA for this thing, I need to worry about what goes on the stack and what things are taken off of it. So if I have AVN, BVN with n even, how am I going to make a PDA for that? And I mean, it doesn't seem immediately obvious how to. So let's go over the other language that we talked about in lecture as well. So very similar, our canonical non-regular language, AVN, BVN, or any n, essentially. So how can I make a PDA for this? If I make a PDA for this, then maybe I can modify it for here. So how can I make a PDA for this one? Well, maybe, let's see. If I have a bunch of A's in a row, and the same number of B's appearing afterward, remember, same number, doesn't that mean that each one of these A's is mapped to exactly one of the B's? Yeah, and none of them overlap, obviously. So maybe what we can do is utilize the stack to our advantage by putting all the A's on the stack and match the B's up with the A's that are on the stack. And if they match correctly, then we say accept, otherwise we don't. What's the problem with that idea? What if we had A, B, B, for instance? I put that A on the stack, and I match the first B up with that A, and the A goes off the stack, but I have this other B. But the stack is what? It's empty. And I can't pop an empty stack. So, and I wouldn't want to recognize this anyway, but how can I avoid that problem really easily?
With like a dollar sign marker?
Yeah, if we put some bottom of stack marker on the bottom, then once we have read through the input, and if we've matched everything correctly, the only thing on the bottom is a dollar sign. And we can't detect if a stack is empty. So that's the basic fundamental flaw that we can fix by putting a bottom of stack marker. So what do you think the very first thing I should do is in making a PDA for this?
Put it on.
Put it on, yeah. So we gotta, for every transition, we gotta decide three things. What am I reading? What am I popping? What am I pushing? What am I reading on this transition? Or should I read?
You're reading just epsilon.
I should have epsilon. Why? Because reading only corresponds to putting the A's on the stack, and for the B's, reading off whenever I see an A on the stack. So this is not one of those times. So I need to say that that's an epsilon reading transition. Should I pop anything? No, because the stack starts out empty, I better not pop anything. And there's no use doing popping there anyway. But am I pushing something? Yeah, some special symbol. I could put pound sign or any other sign other than A or B, because A's are going to go on the stack. So I'm just going to put something other than an A there. Okay, so now we have this bottom of stack marker, so that's good. What am I going to do now? Yeah, if we read an A, what should I do? I should push it onto the stack. Should I pop? No, because there's only a dollar sign on top of the stack. But once I read this A, where should I go? Should I just stay here or go to some other state? Well, if there are a bunch of A's in a row, I'm going to do this operation repeatedly. So what do you think I should do? The self loop. So that's what I'm going to do. I'm going to self loop. I'm going to read an A, and as we said, we're not going to pop anything, and we're going to push an A. So as long as we're seeing A's on the input, I'm going to put them on the stack. Okay? Well, once I read all the A's, what comes next? The B's. So in our idea with the B's is, as long as we see an A on the stack or read, if we read a B on the input, then we should pop an A off the stack. But here, I need to think about what I'm going to do here in terms of the B part. If I just stay here and loop on doing that thing with the B's, then I may have A's afterward. And here, I don't want that to happen. I only want A's followed by B's and nothing else after the B's. So I need to go somewhere else. But what should I do on this transition?
Read the pop A push nothing.
We could do that. So we can read a B, pop an A, and push nothing. But what's the problem with this?
There has to be something that's set.
I'm not worried about accepting yet, necessarily. But what string am I emitting from the language if I do this?
Empty string.
Empty string. And I said that n could be empty, could be 0 here. So what do I do about this transition?
Just make it all just.
Well, as I just said, I can't read anything because I need to accept the empty string. But should I pop then?
No.
No, because the only time when I pop is when I'm reading B. And I'm not reading here, so I shouldn't pop anything. And this is just my turn to make our lives easier. I call this a triple epsilon transition, but you can call it whatever you want. Okay, so another way of looking at this is that once I'm done reading the A's, I non-deterministically choose to come down here to start the B part. Well, once I'm here, what should I do?
Read a B, pop an A.
Or read an A and pop an A, and as always, push nothing. So push nothing. And then once I'm here, let's just say I've matched everything $100% correctly. Then what's on the stack now? Dollar signs. And how do I detect if dollar signs on top?
$, push nothing.
I have to pop it. I don't have this peak operation, remember. So I have to pop in this particular case. So should I read on this transition? No, because the reading should have happened in these two states. I'm going to pop dollar sign. What about pushing? I mean, I don't have to push, but could I push? Yeah, there's nothing in terms of PDAs that says stacks have to be empty when they accept, but they have to start empty. So I could push something there, but I'm nice. I clean up after my messes, right? So I don't push anything. And obviously here I accept because that's the indicator that we have read everything correctly. Okay? Does that make sense? So the essential idea is use the stack to our advantage by putting A's onto the stack and then match the B's up with one of the A's. But the problem is I have this language, not this one. So how do you think I can modify my PDA to work with this guy? So here all I'm enforcing is that the number of A's and the number of B's is even. That's all I'm enforcing. When I first take this transition here to this state, how many A's have I seen? Don't say one. None. I've seen 0 A's, right? Is 0 an even number?
Yes.
I hope so, yeah.
But you made one that accepts it, we'll make another PDA that makes an even amount of, or accepts an even amount of A's and then do the power set construction with that?
Yes, you can. Because there's a problem in CSE that says that if you have a context-free language and a regular language, their intersection is context-free. So you are right, you can do that. But I'm going to do it in place here. And another important thing, since we haven't shown the conversion from PDA to CFG yet, I can't claim that if I have a PDA, I have a context-free language. Necessarily, because we haven't done the conversion. But you will be, after probably tomorrow's lecture, correct. But if I want to do this in place, what can I do? Well here, maybe this state should represent I've seen an even number of A's. So that means I need another state that represents an odd number of A's. But could I push or pop or read 2 things on the same transition? Or can I do at most 1? Well, look at the definition. How many things can I read right here? Either 1 or 0. Pop 1 thing or 0, push 1 thing or 0. So I can't do this in one transition, so I'm gonna make another state. If I could, I would have done a self loop, but I can't. So I can't have, I'm not in that language anymore, so I need another state. And how are these two states going to relate to each other?
They're gonna go back and forth.
So they're going to go back and forth, right? Here represents an even number of A's. If I read one, I should go to here. If I read an A in this state, I come back here. So for these two transitions, what should I pop, if anything? Nothing, right. They're the same transition, just twice. What about pushing? I better push an A, right? Just like before. So if I get to here, then I must have seen an even number of A's, whatever that number is. If I'm here, it's an odd number for sure. Then I come down here, I need to recognize the same number of B's as A's. Do I need to do that same trick with even and odd number of B's?
No.
I mean, I could, but do I? No, and why is that? Yeah, they would have to match up. If I'm here, I must have an even number of A's, which means if I got down to here, I still must have had an even number of A's. So if for them to match up, the number of B's must be equal to the number of A's, and therefore they must be even. So I could have another state here, but I don't have to. Cool. But so therefore we have a PDA to this. Any questions about how we were able to make this? Yeah.
So how do you know push?
On which transition?
Like on when you have the, I guess, fourth stage? Like
Here?
One right before that.
Yeah.
So do you just make A, like, you push A? You push
No.
epsilon, you hop A, push epsilon?
Yeah, not push epsilon, push nothing. Right. So all I'm doing here is if I read a B, I pop an A, don't do any pushing at all. Yeah. We could, just a second. If I push something there, then the next A I want to get to is below the top and I can't do that. So another question? I guess not. Yeah.
So if the language A, B, show that by having those transitions A,
So you're saying if the language was exactly one string in it?
No, if it was like what we just did, it was 2B and 1.
Oh, okay. So so if I said 2n here, yeah.
Yeah. The other way around, we just have it so that the one transition pushes A on the stack, and the other transition on A leaves out.
Well, if I have 2n with n even, then I can't get away with this because I can get here with 6 A's, but I don't want 6. Right? If as long as I kept n as even here. What I could do is, since 2n just means divisible by 4, what I can do is I can have 4 states, 1, 2, 3, 4, which means reading 4 things to get back to here. So if I'm here, I have read a number which is divisible by 4 number of A's. Okay? So it really depends on the problem you're looking at. Any other questions? Okay. So let's look at this one. I want all the strings in A, B star such that the string is entirely A's or is of the form the problem we just did. Okay? So what word seems to be very important here? Or. What do you think that corresponds to? Union, right? Okay. Could we do union with PDAs? So let's just do a little warm up. How do I do union with NFAs?
New start state.
Yeah, new start state, yeah.
Epsilon transition to old start state.
So whatever things I had before, I epsilon transition to both of them. So here, I need to, if I want to do this for PDAs, I want to worry about what happens to the stack. So for these two transitions, should they pop? No, because I start here empty, and therefore I would have a problem if I popped. So I better not pop anything on either transition. What about push? Let me ask you a very important question. When PDAs start up, what is their stack contents? Empty, right? So if it's empty, it's expecting it to be empty when it starts up. So when I take this transition here, the PDA here is expecting it to be empty. Whatever it's doing, I don't know. But whatever it's doing, I expect it to be empty. So should I push there? No. It's kind of like if you have an API to follow, and it says that the API follows this specific set of requirements, you better adhere to the requirements first, and not adorn some other things on it, and it could break at that point. But so that's good. We can do union with PDAs. So if we can make a PDA for the first part and the second part, I think we're good. Well, we already made one for the second part, so I'm just not going to redraw it, and I'm just going to say that this is the PDA from number 1. And that's the nice thing about PDAs, because the drawings can usually get a little messy. I can just copy and paste things because we're just doing union here. But now I got to make a PDA for consistent. Yeah, go ahead.
Do we not need a end of empty stack marker?
No, because I assume this PDA is a valid PDA. I don't know what it's doing. Well, actually, since I already built it, I do know what it's doing. But in general, I can just copy and paste it here. Even if it does absolutely nothing, it's still a valid PDA. So it's still in the union, because it could choose to go down there or up there. Okay. Any other questions about this? Okay. For consist entirely obeys, how can I make a PDA for that? Right, so is that part regular? Consist entirely obeys. I think that's A star. It's a regular expression, so therefore it's regular. So what state should this be that it goes to? Is the empty string consist entirely obeys? Yeah, so we'll have 0 of them. So from here, what should I do? Self loop on, if I read an A, then therefore it still consists entirely of A's. What about pushing or popping? I mean, I could push an A if I wanted to, but am I going to use that later? No, because I'm just going to stay here and loop indefinitely. Oh, I mean, I could push an A, but it's not necessary. Oh, A star is regular. Could I say something about any regular language then? Suppose I have any DFA or NFA. Could I convert it to a PDA? Yeah, how would I do that? Yeah, just don't use the stack. Do the exact same thing here. Just adorn epsilon to epsilon right onto the transition, and now you have a PDA. So the really nice thing is that I can do a very simple transformation to show every regular language is recognized by a PDA. So that's a really nice proof. But did you see how we were able to do union and do the I guess the first part? Any questions about
So do we have to split up the union like that, or like is it possible to use the one from number 1 and add transitions from the A to that final state? Pulling the $sign?
I definitely could, but the problem is that in general it might not work because the stack contents could be different at any given time. And if I had some, in this case it'll be fine because here I don't care what happens to the stack.
Mm-hmm.
But in general, this thing may, if it's a normal PDA, may have something to do with the stack. And if I come over to here, then it'll have a different stack contents. And that's, yeah. And go ahead.
This first one though, not even using the second. Like where do you go, you put the $sign in and you have the A, epsilon
Yeah,
operator push
yeah,
down.
so actually both of these can transition back in this particular case,
Okay.
but in general it might not necessarily work.
Okay.
And something we'll show, context-free languages are not closed under intersection. And way of seeing that in terms of PDAs is that if I did something like the product construction that for DFAs where it does work, the problem is stack contents might conflict. And I can't guarantee anything about what the stack contents are for two different PDAs. So, and that's something we'll show eventually. But do you see how we were able to do union and all that? Any questions otherwise? Okay, let's do the third one. So we have a CFG with start variable s and two variables. And the question says, convert this thing into a PDA. And that was something we showed. We didn't show the other way. We did show how to convert a CFG to a PDA. So how in the world am I going to do that? How am I going to convert these variables and stuff into states and stack transitions? How am I going to do that? Well, let's look at a derivation in this grammar. Maybe that can give us some ideas. What does a derivation in this grammar have to start with? S, the start variable. Yeah, it always starts with S. And that's something that'll actually be very important. Well, maybe I apply S to the three A's on the right-hand side. And then which of these A's is going to get replaced? I mean, in a leftmost derivation, we would replace the first one, but I could choose any one of these. It'll actually be very important I do leftmost derivations here, because the conversion will not work if I don't do leftmost derivations. So I do the first variable A, and let's say I apply BACS to that A, and then I still have the other two A's. So this is the B is a terminal, so therefore I have to replace the first A. And let's say I apply A to epsilon, so I have BCS AA. And then now I got to apply S to something. Let's say we do the other rule, S to little a, big A. BCA, big A, big A, big A. And then now for simplicity, let's say that the big A goes to epsilon all three times. And by the time I get down to here, I have a thing with only terminals in it, and therefore I'm completely done. Okay? So that's a derivation of a string in this grammar. Now, I gotta think, how am I gonna use the stack? Maybe I can mirror this somehow on the stack. So, maybe what happens is I put S on the stack. And then we gotta somehow put these three A's on the stack. Well, how am I gonna do that? Well, if I'm gonna do that, is this S to 3/8, is that a replacement of S? Yeah, it's a replacement of S. So what's gonna happen to this S on the stack? It's gonna be axed off, right? So the stack contents are gonna be 3A's now. Okay? Now, which of these A's is going to get replaced? The top one, because I have only access to that thing. Oh, which of those three A's right here do you think is the top one on the stack? It's the left one. So I want the left side of the rules to be on the top of the stack. So this guy's going to get replaced. The other two are not yet. So I have the two A's, followed by, I need BACS on the stack. So what thing should I push first? S, right. Because I want this side, the left side, to be on the top. Let's see if I do this right. So I have this on the stack now. Oh, but there's a terminal on the stack now. I can't do a replacement. What am I going to do? Well, what should I do? I want to pop it off, but could I just pop it off like that? Or do I need to do something else? What do PDAs have that CFGs do not have? Well, a stack, but what fundamental thing is different? Starts with an I and ends with input. Right? PDAs have an input, right? And it has to be matched, it has to be read somehow. So what do you think I'm going to do if a terminal appears on the top of the stack? It's going to read and pop it off at the same time. And if a variable appears on the top, I'm going to apply a rule and change the stack content accordingly. And if I go all the way through the string and nothing is on the stack anymore, I should accept. Because if there's a variable on the stack, I could apply a rule. If there's a terminal, then since I've read the whole input, I should reject my input. Okay? Is there a fundamental problem though? There always is, right? But what fundamental problem is there? Popping a what stack? Empty stack. So, how can I fix this? $sign on. Right? And once I've matched everything up, what's on the stack? $sign. And that'll be our way to determine we should accept at that point. Okay? Any questions about this idea? Okay. So let's actually make a PDA for this thing. So what do you think my very first action is? Pushing $sign. Should I read on this transition? No, and I definitely shouldn't pop, so I'm going to only push $. Okay? Now, what do I do? Is there a variable or terminal on the top of the stack right now? No. Oh, so I can't do anything then. But is there something I could do?
Absolutely.
I should push what on the stack? Start variable. What does every derivation start with? The starting variable. So I should push that guy out. And I still have this mistake. And now we have a terminal and or a variable on top of the stack, and now we can proceed. So we need to handle those two cases. Either we see a terminal or we see a variable. So the terminal one will actually be easier, so let's do that one first. So if I see, let's say, a little a on top of the stack, what are the things that I need to do? I need to read an A and pop an A. The same character or a different character? Same character. Because the terminals that I produce in the derivation correspond to the string that I want to make, which is going to be in the input that I provided as the for the PDA. So I need to pop it off the stack. So I'm going to have one for each of the terminals in the grammar, which is little a, little b, little c. So I'm going to have read an A, pop an A, push nothing. Read a B, pop a B, push nothing, and same thing for C. So I'm just going to let you know right now, these three transitions are the only transitions in the entire PDA that read. No other transition reads. Okay? Well, we handled the cases when we have a terminal on top of the stack, but now we got to handle the cases where a variable appears on the stack. So either an S or A could appear on top of the stack in this case. So let's say I wanted to apply S to 3 A's. How did we do that conversion here? In terms of the stack here. I pop the variable on the left side, then what do? Push the right side of the rule, but what order?
Reverse.
reverse order because we want the leftmost contents of the right-hand side to appear on the top. So that's what we're going to do. But could I do this in a single transition, push those 3 characters? No, since I can only push at most 1 character. So I think what I need to do is come out and then eventually come back to this looping state. So should I read on this transition?
No.
No, because I'm not generating any characters by popping a variable off. So I'm going to read nothing, pop the S off, and I better push nothing here. I could push an A right here, but what I'm going to suggest is that you separate the part which represents popping the variable and pushing the right-hand side. I could push an A right here, but I want to separate those things. There's nothing wrong with merging them like that, though. Okay, so now I got to push the 3 A's on. Well, since they're all the same variable, I don't care which order you do it because it's the same variable. So I'm going to read nothing again, pop nothing, and push an A. Come here, epsilon, epsilon, A, epsilon, epsilon, A. And since I pushed 3 variables now, I can just do a triple epsilon transition back. So I'm going to do triple epsilon back. And I know some of you are going to think, well, couldn't you just delete this transition, this triple epsilon, and make this guy come back? Yes, I can. But what I'm saying is that I'm trying to separate the duties. The part which represents reading off the input, the part which is popping the variable off and then pushing back on. But there's nothing wrong in making it go immediately back. Okay, you see how we did that? Okay, so we did the first rule. Let's do the second rule. So which of these 2 should I push first? The big A, right? I want the little a to appear on the top of the stack, so I should push it last. And the nice thing here is that the same variable appears on the left-hand side. So you may think, well, I'm going to take this transition here and then go off in a different path and come back. I could do that, but again, I want to separate everything so that I know exactly what I'm doing. And it'll be nice if I separate them because each one of these paths that goes out and comes back represents a single rule in the grammar. So I'm going to have another path out, which represents popping the S off. Then I got to push big A first. So epsilon, epsilon to big A first. Epsilon, epsilon to little a, and then triple epsilon my way back. Okay, the same procedure as before, but just with different things to push. So that side's done. So now I gotta handle the 2 rules for A. So I could apply A to epsilon, and that one looks easier, so let's do that one first. So I need another transition out. Again, I'm not going to read. I'm going to pop an A this time, not an S, because A is on the left-hand side. And here, I don't need to push anything, so I can just immediately come back with the triple epsilon, because I pushed nothing. Okay, that was pretty easy. So that one's done. And then now I got to handle this long rule. So which one of these am I going to push first? Push first. S, right? The thing I want on the top is on the left side. So I want B on the top, so therefore I should push S first. So I'm going to do exactly that. So epsilon, pop, and A off. Push nothing. So epsilon, epsilon to, the thing I'm pushing is S. Epsilon, epsilon to C. epsilon, epsilon to A again, epsilon, epsilon to B, and then triple my way in. Okay, so all we're doing here is that each one of these paths that comes out and comes back represents a rule. This is the first rule, second rule, third rule, fourth rule. And we're popping the corresponding variable, push the right-hand side in reverse order. So we get exactly the derivation we want. Am I done? What's the language of this PDA as is? It's empty because there's no final state, right? So when should I accept? Or when an accepting a condition occurs? Well, if I'm here and a $ appears on the stack, and what else is true about the input? If I've read the whole input, should I be done? If I read the whole input and I matched everything up correctly, should I accept at that point?
Yes.
Yeah, but how do I detect that I matched everything up correctly? The $sign's on top of the stack, and that's the only way I can determine that. So I should pop it up. Again, I can push something, but I'm not. Okay. Yeah.
I just don't understand all the self-loops. Why are we popping C, B, and A?
Because when we remember, PDA has an input that's provided. So, for example, if I provided this PDA with B, C, A as the input, it better accept because that is in the grammar. So whenever I produce a terminal on top of the stack, then that terminal in the derivation is never going to be replaced by anything, right? So what I could do is just read it off the input. So it's on top of the stack, it's on the input, I'm just gonna read it off.
When did it get pushed on top of the stack?
When I applied one of these rules. So like in one case, it would be here, the last thing that was pushed was a B on top of the stack. So the ones that happen to have a terminal at the start, they will do the self loop right as they get back. Because there's no other thing that we can do at that point. So that's really nice. The only thing, the only times that we could possibly read are right here, and that corresponds to producing a terminal at the beginning. If there's a terminal in the middle, I don't care until I eventually get to there, at which point I'm going to read it anyway. And then the problem is, so there's a problem with this, in that could I possibly get to that accept state without having read all the inputs? And actually the answer is yes. Consider AB, the string AB. It's not in the language of this grammar. Because if I produce a B, I better produce a C. So this is not in the language of the grammar, but is the string A in this grammar?
Yes.
Yeah, I can just apply S to this guy, and then A goes away. And so if I write that down, then what happens to the stack? Well, the stack starts off with $ and S on it. Then I'm going to axe the S off. Then I'm going to push this side in reverse order. Then we see that there's a terminal on top of the stack, so I'm going to read it off the input and pop it off the stack, according to this. So the thing I have left is $ and A, big A. Then I apply A to epsilon, so that guy's going to get axed off the stack. And then we see, oh, there's a $ on top of the stack, so therefore I should go to the accept state, and I can go to that accept state. But will I accept? No, then why not? I haven't read all the input. So we have this fail-safe in that we won't accept until we've read all the input. If we've read all the input, the only things that could happen are there's a $ on top of the stack, which means I could accept, or there can't be a variable because if there were, I would have applied a rule, and if there was a terminal, then that means that the input is not in the language of the grammar. And so I get exactly what I want. Okay? Because it's non-deterministic, it will choose the right answer if there is one. So I do get exactly what I want here. So are there any questions about this? I think I'm out of time, so are there any last questions? All right, I'll see you next week.